Hello, this is the Chapter 15 video podcast, Part 1 for Field Methods in Hydrology about lakes and estuaries. Now, it isn't so much that there's something particularly special or different about sampling in estuaries compared to what we've already talked about in general with different technologies or for rivers specifically with what we captured before. But there are some unique aspects, and really it's just a good opportunity to think through how we apply hydrology in a setting that we haven't looked at yet. And in this case, we'll look at lakes and estuaries as two of the other, large, open, freshwater areas besides what we've already looked at with streams. I'm breaking this into two video podcasts, one dealing with lakes, the other is dealing with estuaries, but it's really they're just different examples, and I'm not going to be repeating the same material, but looking at different issues. And of course, if you've never been introduced to these settings, then this will be a chance for you to learn something about them. Of course, we're going to focus on water and energy balances, circulation patterns, water quality issues that are unique to each of those settings, and then I'll give a case study for each one based on my own experience. Whenever we look at hydrology and you're ready to go on the field, the first thing you should be asking yourself is, what is the water balance? This is hydrology. We do water balances. Never forget that. Always begin there after you've done your historical analysis and you have an idea of what's going on. This is a generic water balance. Again, it can be written anywhere, but there are some unique elements of it that we'll think about for a lake. So here's a little schematic of a lake, and we've got change in volume through time. Here V is not velocity, but volume. So the total volume of water in the lake through time is changing. You have a vertical water balance between precipitation in and evapotranspiration in. And here, like L here, it means over the lake. The precipitation over the lake and evaporation over the lake, that is turned into a volume by multiplying it by the area of the lake. Okay, so this might be like millimeters per hour times how many square millimeters of the lake, and that'll give you that total volumetric flux. There also could be surface water in and surface water out. Now, surface water in is going to be heavily influenced by the size of the watershed feeding the lake. Disproportionately, the bigger the watershed, the larger the role for inflow compared to precipitation in affecting lake processes. There could also be one or more outlets or no outlet, depending on the nature of the lake. Similarly, there could be groundwater flow discharging to the lake, and the lake could be a source of recharge into the groundwater system, and that would have to be looked at. Now, in terms of field measurement and technologies, we've already looked at precipitation, we've looked at flow on the surface, and to some extent we've looked at volumetric change in that you can just put pressure transducers here, and we will still be talking about them more, but you're pretty familiar with them. So you can monitor water level and thus volumetric changes through time. We haven't yet dealt with evapotranspiration or groundwater fluxes, and so those will be coming soon. An important thing to understand about hydrology is that although we're primarily interested in the water balance, we often have to supplement that with an energy balance. That's because there are certain components of the water balance that may be easier to ascertain with an energy balance than with a water balance. And most specifically, I'm talking about evaporation. Evaporation is both a water flux and an energy flux, and we will be dealing with it more later in the quarter. But for right now, let's just look at the energy balance. So here E is energy, not evaporation, but energy. So energy is stored in the lake. It's not just temperature, but it's the actual energy in the lake. And the change in energy through time is a function of different inflows and outflows. So it's just, again, same kind of budgeting. Now we can look at the different kinds of radiation, like long wave radiation, short wave radiation. We also have heat flux that goes through evaporation and conductivity, and also through mass flux changes. So I bet some of you are getting a little nervous right now because this may be your first time looking at an energy balance. And so therefore, it's going to take a little more work, but those of you who took my course HYD 143 will remember we also had a couple of scary lectures about energy fluxes, so this is sort of a capstone on that. So first we look at the radiative terms, the long wave radiative terms, and we see that the sun is providing the Earth with energy. Some of that is taken up into the atmosphere and also reflected back down at the Earth. So we have energy coming down to the ground directly from the sun as well as from the atmosphere. And then that is balanced by long wave radiation leaving the lake. And we can take those fluxes and lump them all together in what we call net radiation or net long wave radiation. Besides that, we have evaporation, which is a loss of energy. We have what's a short wave radiation or sensible heat flux. When you look across a road and you see the shimmering of the light, okay, that's sensible heat flux associated with that change in temperature over that surface. There also can be conductivity. Conductivity is when higher energy particles are moving around a lot and they're bumping into lower energy particles, and that creates a direct transfer of energy from particle to particle. So these are generally going to be losses, not always, but anyway, they are fluxes. And then it also turns out that there is energy held up in rainwater or stream flow and groundwater that are coming in and out of the lake that one has to be mindful of as well. Besides the basic energy fluxes, it's important to be aware that if you're going to do a monitoring program for a lake, there's a whole variety of circulation processes, vertical processes, horizontal processes that are mixing up conditions and creating complexity. Now, I'm not going to ask you on a quiz or anything like, what do all these different things mean? But the main point is to just understand that there's a lot of things about how water moves around, driven in combination with sediment, like a turbidity current, or as a result of wind energy creating lots of mixing, changes in heat, and other things. For example, if we just look down on the top of a lake, like here's a lake, Lake Biwa, you can see here using blues and reds circulation patterns of the lake predicted using a computer simulation, I believe. So it shows a very complex pattern, largely driven by the wind dynamics that are taking place, but also guided by the topographical steering of the shape of the lake. One of the ways to get at that is with what are called drift buoys. Here you put out something that's going to float, which in this case we call a buoy, and you can put a GPS on it, usually a differential GPS, and then you can let it go, or you can be tracking it so that you can see where it goes and then eventually recover it later. If you can put out enough drift buoys, then you can really learn a lot, and that gets back to the environmental tracer presentation that you already saw. Another way is to use an anchored buoy, and with an anchored buoy now, it's staying in a fixed location, but you could mount velocity sensors, water quality sensors, onto the buoy so that as water moves past it, you'd be characterizing its speed, direction, and attributes. Of course, both drift buoys and anchored buoys are relevant in estuaries, lakes, reservoirs, even large rivers. So it's not just for lakes, but I'm just introducing them to you in this context. It's also important to understand that when you want to look at the water quality of a lake, there's a fundamental control on that you have to be mindful of in terms of how you're going to stratify your sampling. And that relates to the vertical stratification that's present in a lake. Lakes exhibit a vertical stratification, usually with 3 layers. A surface layer called the epilimnon, which is generally warmer, low-density water. A zone of rapid temperature change called the thermocline, and then the cold, high-density deep waters that's called the hypolimnion. How does this all work and take place? Well, of course, the primary energy that's getting into a lake is coming from above, whether it's directly from the sun or through water exchange or wind. It's all being gained or lost through the surface. And as you can see here, the y-axis is water depth and the x-axis is temperature. So we can see that during some parts of the year, the surface can be extremely warm, and at other times of the year, it could be essentially frozen. We could have ice on the water surface. You could also imagine that this is going to be strongly influenced by where in the world you are. So if you're in a tropical climate, it might be perennially warm and therefore a very stable system. However, if you're in a place with a lot of seasonal changes, cold winters, hot summers, then you're going to have the kind of change that's illustrated in this graph. So if we look at the temperature distribution with depth, you can see that it's high temperature at the surface, dramatic change in the thermocline, and then a low temperature through the bottom. Remember that associated with temperature is water density. Temperature, salinity, gas concentration, those are the main things that are going to affect the density of the water. And we use the word like pycnocline to mean the gradient in density. Got some birds overhead here. It's kind of annoying. Okay, so we have this density gradient. So warm waters are low density, cold waters are more dense. And so therefore in the summer we get a stable stratification of lake temperature. However, as we go from summer to fall, the surface cools rapidly and it'll eventually get cooler, lower temperature, higher density than the deeper water. And as soon as that happens, then that surface layer is going to sink, and that's going to create mixing of the lake. Then, if it gets to a freezing condition, it will become low density again. So it actually inverts again, but ice will be floating on the water surface. And then in the spring, as soon as that ice melts, you now have ice in the 1 to 4 degrees Celsius range that's more dense than the deeper water, and you get another turnover. So if we look at it from vertically, this shows the same process. In the summer, light blue is indicating warmer conditions, dark blue, cold. Then in the autumn, we get a mixing as the surface water cools down. Stable stratification in the winter with the ice cap, and then a turnover again in the early spring when the ice melts. Now, if you think about how you would sample a lake if you're interested in water quality, you've got a variety of problems. You've got the surface pattern that could be there. Are there places in the lake that might become quite stagnant and not well mixed, might have very long residence times? And same thing in the vertical. If you only take surface samples and you don't take samples through the depth, or you don't take the time to find the position of the thermocline and therefore properly stratify and do equal effort sampling above and below the thermocline, or maybe to just carefully characterize the thermocline itself, then you're going to run into problems with how you achieve the goals that you want out of your monitoring program. So that's why I'm taking the time to show you this information. There is a sensor that's relatively uniquely used for lakes, but it could also be used in estuaries and rivers too, called a Secchi disc. This is a device that you see here. It's alternating white and black, triangles or whatever sectors of this disc, and it's suspended by a string on this eye bolt. And then what happens is you lower this down in the water until you can't see it anymore, and then you very slowly pull it back up until you can just see it underwater. And the rope that you use to lower that down should be graduated in some way so that you can then measure the length of it one way or another so that you know what the water depth is right at the point at which you can just see that. So a lake that has a lot of clarity, you're going to get a much deeper Secchi depth reading than one that has a lot of turbidity. It's possible that this reading is not just a function of turbidity, but it could also be influenced by the color of the water too, so that's important to understand. So this is a measure of clarity more than turbidity. This kind of observation is subjective, and it does depend on interpretation. Different people have different eyes, different capabilities, or just ways of interpreting what they see. And then, of course, one person over their lifetime their eyes are going to change. So even having one person read year after year doesn't necessarily mean you're getting the same outcome. However, this is really useful information in guiding management decisions and especially sampling when there's research you need to do that's sensitive to lake clarity. So if you were doing some kind of snorkel observation or wanting to record high turbidity or low turbidity conditions, you could use a Secchi depth reading to get information about when you should or should not sample. So having the ability to make a rapid assessment as a first step to condition when you're going to actually get the real data you want is a good way to use a Secchi disk. However, using the Secchi disk itself as the basis of management, I would say would be a poor decision. And that's because we have other technologies that we can use, such as a water turbidity sensor. Again, this would be focusing more on turbidity than on just clarity, but it is highly overlapping. And I already presented a turbidity sensor to some extent when we addressed water quality at the outset, but I just want to look at it again and note that there is a strong relationship between turbidity and the kinds of problems that different organisms such as freshwater fish can face. So a turbidity sensor such as the one illustrated here is about $2,000, and it costs a lot for the cable depending on the kind of sensor it is. And don't forget, you have to have a data logger and all the accessories that go with that. I also want to just show you an example of installation of a turbidity sensor. So here's a case where adjacent to a water body there's a concrete, like a bridge and a wing wall here. And so that's a really nice place to bring the turbidity sensor down in an electrical conduit, which then goes to a flexible electrical conduit. We have these metal straps that are holding this down. You can see that there's a pressure-treated lumber board bolted to the concrete with 4-inch cement screws. And then the turbidity sensor is inside this plastic housing with only the face of that sensor showing. And then the sensitive part of it is facing perpendicular to the current in this case. Now, of course, if the current is very complex and maybe flowing in a lot of different directions, it may not be easy to do that, so you just have to do the best that you can. Turbidity sensors are subject to what we call biofouling, which means that things are going to grow on them, and so you have to clean it off. And how often you have to do that will depend on the water temperature and climate, water quality conditions of where you are. If you're in a very cold and clean setting, then it may not require cleaning more than once every 2 weeks or so. Whereas if it's in a setting where it's very warm, then you're going to need to clean it much more frequently than that. Also, you can see these weird looking bottles here. These are called single stage suspended sediment samplers, so that when the water rises up, then they'll be able to collect samples associated with that through this siphoning mechanism. And that will allow you to get samples at different stages that you can then use to compare the suspended sediment concentration in the sample with the turbidity reading that the sensor gave at the same time. Okay, well, there also are a variety of water quality sensors, and it's very common now to see automated sensors where you have a sensor platform with up to 9 or 10 interchangeable parts with different sensors on them. And here's one example. This sensor, we've got a dissolved oxygen sensor, a turbidity sensor, and notice that this one has a wiper, so that wiper helps to keep this clean automatically at the expense of course, a lot more money and mechanical parts that can fail. We've got some sort of conductivity or total dissolved solid sensor, possibly a pH meter or oxidation reduction potential meter, and then you can have electrode specific or ion specific electrodes doing nitrate, ammonia, chloride, or other constituents. So this is a fairly typical thing that you see, and the trade-off is just depending on the size of the lake, the more of these that you're shoving onto the platform, then hopefully the larger water body you have to make that worthwhile. It's also important to be able to sample water from a lake, and of course you can always go to the edge or off the side of a boat with your hand and put the bottle in and get all the air bubbles out and cap it underwater. But you can't control the depth at which you're going to sample, and you could have a lake that's 100 meters deep. What if you want to sample from 52 meters water depth? The answer to that is primarily to use something called an alpha sampler. This is your single depth sampler. A Chemer sampler is also similar. What's happening here, you can't quite see it, but there's elastic tubing between these two plungers. And you can see that the plungers are bent up, and then there are cables that are attaching onto this metal part on the top. What happens is you have a line running through the center of this metal bar that goes back to your boat or off a bridge or whatever. So you lower that down in the water, just lower that out to whatever depth you want, again using like a graduated rope or whatever. Lower that down, and then you take something that looks like a metal bullet, like the size of my fist. You put that onto the line, and you drop that. When you let that go, the weight of that moving over the rope is going to go all the way down and smash into this. When it smashes into the alpha sampler at the proper depth, then that trigger releases the cables on either side, and because there's an elastic tube in here, it springs shut and closes the bottle. The Chemer sampler is vertically aligned, but it works the same way. You send down something, a heavy weight, we call it a messenger, and when it hits the bottle closes. The Niskin sampler is a far more sophisticated tool for lake sampling, and it's one in which you can not only have one bottle, but you can have a lot of bottles in line. So when the messenger hits the first bottle, that not only triggers that closed, but it then launches another messenger down to hit the next bottle, and you get a chain reaction like dominoes, so that you can close many bottles in a string, roughly the same time. So these are some standard approaches. Alpha samplers are readily available for a couple $100. They come in a variety of sizes, and they allow you to get this single point depth measurement of water quality. If you're on a boat, then it's really easy to deploy. The only caveat, though, is that if there's a lot of current where you are, then of course as you're lowering the rope down, the alpha sampler is going to catch the current, and it's going to be pulled in the direction of down current, which means it may not be straight down. So if you're trying to go 50 feet and you let out 50 feet, you may be going less because it's at an angle, not straight down. So that's an important constraint. You could also use this in a river off a bridge if you want to get a sample, again, depending on the current. And of course, you can always add a hefty weight to the bottom of an alpha sampler to ensure that it stays more vertical. A more elegant, though fragile solution is called the glass tube sampler. This has been used in lakes fairly deep even. And imagine, the old McDonald's straw trick. So, you go to a fast food restaurant, you order a soda, and you come to the straw, you put it in, you put your thumb over the straw, you pull it out, and then you let it go, and it goes into your mouth, and you have a lot of fun. So what you're doing there is you're basically applying a suction by capping that so the water can't go out, because as it's trying to fall with gravity, it creates a void, and until the pressure in that void is equal to the weight of the water, so it can't go down. Well, this is the same thing. Imagine instead of one straw with a cap on it, imagine a whole string of straws, but the cap is open. So in this case, it's a glass tube instead of a plastic straw, but it could be plastic too. So you put this whole thing all the way down with everything open. These black, weird-looking things are essentially like valves. And once it's down with all these valves open, the whole thing is full of water. So what you do is you close the top valve. As soon as you close the top valve, you now have locked in that water column in the whole tube. You then raise it up until you get to the next valve, close that valve, and disconnect the top piece. sample the water out of the top, and then continue on. So you just keep raising, close the valve, raise, close the valve, raise, close the valve, and you're getting an integrated sample, and you're actually sampling the entirety of the water column all in one shot. So that's a pretty elegant solution, although a little bit fragile and difficult to implement. It's not something that you would commonly see, but I like the novelty of it. I'd like to show you an example of a very exotic form of lake because it has the most exotic chemistry, and so that makes it kind of fun to look at. And these are lakes that sit on top of volcanoes, typically with some level of activity and not just totally dormant. About 12% of the world's volcanoes have lakes, and here's some examples of different kinds of lakes that are shown here. Although Ruapehu looks calm in this particular photo, I assure you it's not calm at all. When you have a volcanic lake, because you have all this volcanic activity, then you can get really, really dramatic chemistry going on. But not just chemistry, but very complex physical and chemical processes taking place. So underneath, you have some sorts of magma. The magma is probably not interacting directly with the water because that would evaporate away too quickly, but that does happen from time to time. And so what happens is that you have you basically hot water and hot gases that are coming up under the volcano that are heavily altering the rock under the volcano, creating lots of fractures and changes to that rock, which then allows extraction of chemicals out of that rock in what we call multi-phase flow. So multi-phase means a mixture of gas and water and possibly some sediment, and that is all moving up, carrying chemicals up. You could also have a situation where you have heat moving up without the flux of mass, and that's because the water is hot, it goes up, rises as steam, cools off, condenses, and goes back down. So that allows the heat to progress without necessarily moving mass flux. Then material comes out into the fractured rock. You may have vents. There could even be pools of exotic fluids like liquid sulfur on the bottom of the lake. And that creates all kind of crazy, conditions of, highly acidic conditions in the lakes themselves, accelerating the processes. So let me show you the result of a mass balance and energy balance that I did for Volcanic Lake earlier in my career. So if we just imagine that you have heat rising up into a lake, okay? In this case, we're going to use sulfur dioxide in tons per day as the surrogate for heat. The heat is on the right, is shown here as volcanic input in megawatts. So these two are related to each other in the y-axis. Now, our goal is to be able to predict what is the steady state lake temperature that results from a constant influx of that heat in response to different amounts of water coming out of the atmosphere, what we call meteoric water input. So the meteoric water input would be what we're interested in, and then we have lakes of different radius. So let's start with a really big lake, a 300 meter diameter lake, okay? And we're going to have a meteoric water input, let's just say 3,000. So we're going to go up until we hit that line, and then we're going to come across for that particular input until we hit the same line and then go down, and that'll give us the lake temperature. Now you can put this together in different combinations to get to different outcomes. But one thing you can see in general is that if you start here with different sulfur dioxide inputs, the higher the input you put in, then the higher the lake temperature is going to be. And that's reflected by the fact that these lines move to the left as they go up. Meanwhile, okay, if we look at the size of the lake, you can see like a very small lake, like a 50 meter diameter lake, it gets really hot for a really small amount of energy input. So it's basically just going to evaporate away, and it won't be in steady state anymore. Whereas for a very large lake, you have the ability to quench the heat from a much larger amount of input. Okay, so we can basically work through this to get different steady state water balances. Like if you have a certain amount of we could work backwards. So, for a 40 degree temperature lake, or a 40 degree temperature lake with, say, diameter 150 meter radius, then you can predict that you're going to have a certain amount of sulfur dioxide input to that, and you're going to have a certain amount of rainwater coming in. Another factor about the size of the lake is assumptions about the relative proportion of the watershed area to the lake area. And that's also being captured by the lake radius effect here too. So the purpose of this slide is to just illustrate to you the importance of mass and energy balances in understanding the temperature of a lake. This is true for a normal lake, but it's just exaggerated in a very dramatic way for a volcanic lake, where the temperatures can get very high with even relatively small amounts of volcanic input. Another exotic form of volcanic lakes are what are called bursting bicarbonate lakes. These are lakes that look perfectly normal on the surface. You could be fishing and living around a lake like this and never know. And then one day, such as on August 21st, 1986, while everybody is asleep or whatever, a vast limnic eruption occurred, for example, at Lake Nyos in Cameroon, and that released an estimated 1.6 million tons of carbon dioxide. So you have this just vast bubble, like a burp, of carbon dioxide out through this lake, and then that goes really high up into the air. There is about a 300-foot high fountain of water. Just imagine like shaking a Coke can, popping that open, and just watching that erupt 300 feet high. Your biggest Mentos play you've ever tried. But then all of that carbon dioxide, being denser than air, then fell back down and smothered the surface with carbon dioxide. So all living things that need oxygen to breathe then suffocated because there was no oxygen to breathe, and it resulted in the death of 1,700 people and their livestock. So a pretty dramatic effect. It's a very rare thing. It's only happened in a few lakes in the world, in Africa. And there's been a lot of debate and controversy about understanding this kind of lake. But here's some data that shows what happened after this event took place, when scientists ran down there to go monitor. Here are vertical profiles of temperature. Now look how the temperature is higher at the bottom than it is in the middle. You would expect that high temperature should result in a turnover, right? Like this hot water should be rising. It should be like when you boil water in a pot, that hot water has to rise. But that's not happening. And the reason it's not happening is because of the salinity. If we look here, the microsiemens per centimeter, that's your electrical conductivity measurement, or total dissolved solids, that's also high. And so, in fact, what's happening is that the dissolved concentrations are far high enough so that the density of the water is overwhelmed by that salinity component compared to the temperature and gas content. You can also see, if you look at the bottom right here, that the concentration of carbon dioxide in the lake, we look at the tiniest little specks here. It says November 86. It was the lowest at depth. And over the years, from 86 to 2001, you can see that has increased substantially, showing that a lake like this is capable of holding vast amounts of carbon dioxide. If you didn't notice before, if you look at the y-axis where we have water depth, the depth here is over 200 meters deep. So we're talking about a very deep lake with very high water pressures. What do we have, like 1 atmosphere for every 10 meters or something like that? So we're talking about more than 20 atmospheres of pressure. Just think about how much carbon dioxide you would have in that situation. And you can imagine that if the level of carbon dioxide started to approach the saturation level, all kinds of instabilities could be taking place. whether there's a specific physical trigger like a landslide or a volcanic event or anything like that, it usually isn't even necessary. And this is something that's well known in the oil and gas industry for in their gasoline tanks, and why they have to be very careful about allowing too much vapor to be present in those storage tanks. As a result of that, there is a process of degassing in this lake and in at least one other, where basically they started off pumping water up, and then as the water rises, the carbon dioxide comes out of solution, just like opening a soda can, and then the bubbles rise, and as they rise, then they pull water up from the bottom, creating a siphon effect. And so you can see this giant tower of water blasting out of here. After you prime it, then it basically just goes on its own. And this shows since that began in 2001 to 2006, there has been a subtle decrease in those concentrations. I haven't checked lately. I'm sure you can look at it online. But we are seeing that it is possible to at least try to manage this. Now, you also run into the problem that somewhere under this volcano, there's probably storage of vast amounts of carbon dioxide. So it may be that degassing is just going to increase the gradient in the abundance of carbon dioxide between what's underneath and what's in the lake, which might then increase the rate of carbon dioxide delivery into the lake through the bottom. So, I mean, degassing, it may be necessary to kind of hold the line, but I don't know that you could ever fully empty it out. Or maybe, maybe there really isn't that much stored underneath, and it's just sort of like a trickle in, and as long as you're degassing faster than that, then you can get rid of it. So this is a very interesting, applied, and bizarre, case of managing the water quality of a lake that shows, a lot of innovation that scientists have to do in grappling with an unexpected phenomenon. So overall, when we talk about lakes, we have to think very carefully about the water balance, the energy balance. We have to think about how we're going to sample in terms of the context of vertical stratification processes and horizontal circulation processes. And then we have a variety of different technologies, all the traditional ones we've already talked about, like multi-beam echo sounding, but then some new specific things in terms of these alpha samplers and other ways of measuring water or sampling water in the lakes. So I'll stop there, and then we'll continue on with part 2 in the next podcast.